So today I'm going to talk about the relativistic Doppler effect. It's a very interesting effect, right? So we have also studied the Doppler effect earlier in case of sound. So what here we will talk about the Doppler effect in relativity. So when light source and observer are in relative motion, the frequency of light observed by an observer is not equal to frequency of light emitted by the source. So this change in frequency of light due to motion of the observer relative to source of light is known as Doppler effect. To study this effect, we will here discuss two cases. To study Doppler effect, we will study here two cases. First case is that light travels parallel to the direction of motion of observer and another thing is that light travels perpendicular to the direction of motion of observer. So here first of all let me discuss this when light is traveling parallel to the direction of motion of the observer. So for this let us draw a diagram. This is the coordinate system 1, this is the stationary frame of reference, and here I will take another frame of reference, and that frame of reference is a moving frame of reference, and say this frame of reference is the prime frame and it is moving along this direction with velocity v, and say it is x prime, this is y prime, this is z prime, this is x, this is y, and this is z, and it is s frame. This is a stationary frame. So say a pulse or a plane wave of electromagnetic wave is emitted here, and say it is represented by a cos kx minus omega t. It is the wave representation, plane wave representation of the wave which is emitted from here. right? But observer is moving with velocity and it is moving in the S prime frame, so that means how its frequency seems to be in this frame of reference, right? So here we have considered a plane wave, and plane wave is represented by UA cos of kx minus omega t in the one frame of reference where k is 2 pi by lambda. It is known as wave vector. Omega is the frequency and a is the amplitude. So let us recall now the Einstein's postulate. I will talk about Einstein's postulate later on, but here I will use those postulates. So according to Einstein's postulate of relativity, the phase of the wave must remain invariant under Lorentz transformation. So if I use this, then this is the phase in the rest frame of reference kx minus omega t, and in the moving frame of reference this phase seems to be like this, k prime x prime minus omega prime and t prime, and this phase should remain the same, right? Now let us do one thing, that as we know that x is equal to x prime plus b t prime over 1 minus p square by c square under the root, and t is equal to t prime plus vx prime over c square upon 1 minus p square over c square under the root. So if I put these values here, then this equation will become that x is k x is what, x prime plus vt prime over 1 minus p square over c square under the root minus omega t prime is what, t prime plus vx prime over c square over 1 minus p square over c square under the root. It is its value t prime. Then is equal to k prime x prime omega prime and t prime. Then let us do little algebra. Here 1 over 1 minus p square over c square can be taken outside because it is common in both, and inside we will remain with kx prime plus vt prime minus omega t prime minus omega v upon c square x prime is equal to k prime x prime omega prime t prime. So let us put x terms together and the t prime terms together. So if I do that, then I can write down it is k minus omega v over c square, x prime will be common, minus omega minus kb, it is t prime, and outside it is 1 over 1 minus p square by c square under the root, it is equal to k prime x prime omega prime t prime. So if I put their values, now let me make it more simple. So it is k minus omega v over c square over 1 minus p square over c square under the root into x prime minus omega minus kv over 1 minus p square over c square under the root into t prime. It is equal to k prime x prime omega prime and t prime. When I do this, then if I compare both sides, then what I am getting? I am getting that this k prime is equal to k minus omega v over c square over 1 minus p square by c square under the root, and this omega prime is equal to omega minus k v upon 1 minus v square over c square whole under the root, right? So I am interested to find out the shift in the frequency. So this is angular frequency, so from here I can write down as 2 pi nu is equal to 2 pi nu, and k is 2 pi by lambda, and it is v over 1 minus p square by c square under the root. This 2 pi will cancel out because it is common, so that means this will cancel out, right? So now this is nu is equal to nu minus v over lambda upon 1 minus v square over c square under the root, and this is equal to, since nu lambda is equal to c, so 1 by lambda is equal to, this goes to here, and this is nu upon c, so it is nu minus nu upon c into v over 1 minus v square over c square under the root. So it can be written as nu can be taken outside, 1 minus v by c over, it is nu, it is v over c, 1 minus v square over c square under the root. Let us do little algebra. So it is nu prime, so nu prime is equal to nu c minus v by c whole upon c square minus v square over c square under the root. So it is c minus v by c, v will remain as it is c over c minus v and c plus v under the root, but it can be written as square and under the root, so that means this one part will cancel out with it, right? It's a little algebra, need not to worry about it, you can do it very easily, right? So it is v c minus nu and c plus nu, sorry, it is nu can be taken outside, yeah. So here I have taken nu, it is c minus v over c plus p whole under the root. So this is known as longitudinal effect. This is, and this shows that how frequency changes, and this is known as longitudinal effect. And here, since c by v, c minus v over c plus v is always less than 1, therefore we are concluding that nu prime is less than nu, right? So this is the longitudinal effect. Now another effect when light traveling perpendicular. Next is that light traveling. Next case is that light traveling perpendicular to direction of motion of observer. So here let us draw a diagram again. So if I draw a diagram, then most of the things will be clear from the diagram once we are having a beautiful diagram, right? So let us try to plot it. Yeah, that's what we can do. So it is basically yeah, it is z-axis, it is x-axis, it is y-axis, and here it is z prime axis, it is x prime axis, and it is z prime axis. Similarly, it is traveling along this direction s prime frame, and here it is the s frame. And say a light is traveling along y-axis, means perpendicular to the direction of the observer, right? So it is represented by u is equal to a cos of k by minus omega t is the representation of this wave. It is traveling along this direction. So again, that u is a cos ky minus omega t, but as phase is invariant, so due to the phase invariance, what will happen in both the frame of reference is k by minus omega t must be equal to k prime by prime minus omega prime t prime. So if you put their values, then it is k by prime minus omega prime, sorry, not omega prime but omega, yeah, it is omega prime, yeah, it is omega prime t prime is equal to, or let us do one thing, need not to do it, but what I will do, I will use that it is ky prime as it is, because y prime will be equal to y and omega will remain as it is, but t can be written in the form of t prime, so it is t prime plus vx prime over c square upon 1 minus v square over c square under the root. This is the value of this t is equal to k prime, y prime, omega prime and t prime. It's a very interesting result which will be emerging out of this little calculation. So here let me expand it, omega t prime over 1 minus b square over c square under the root minus omega vx prime over c square over 1 minus b square over c square under the root is equal to k prime, y prime, omega prime and t prime. So since there is no term like this, so that means this should be 0 and these must match each other. So if I compare corresponding y's and t's, then we are concluding that from here k prime must be equal to k and omega prime must be equal to this one, because this is sitting in place of t prime is here and here, and it is independent of these y prime and the t prime, right? So it is omega prime must be equal to omega upon 1 minus v square over c square under the root. That's what will happen. Means the equality of this indicates that these must be equal, right? Then and only then this equality will be applicable. So if I put the values that 2 pi nu is equal to 2 pi nu, it is 1 minus v square by c square under that, this 2 pi will cancel out with that, then nu prime is equal to nu over 1 minus v square by c square under the root, and the frequency thus obtained is known as this is called transverse Doppler effect. So this is all about the Doppler effect which we observe in case of special theory of relativity, right? We have used the Lorentz transformations here. So that's all for today's lecture. So thanks for watching this lecture. If you are find these lectures useful, then you can subscribe this channel and press bell icon also, and so that you can aware of new lectures which I keep on uploading as soon as I will get some time, right? So that's all for